again with a glass stem failure. This failure is just like the crack on the first gun that failed before it. And here's another view of that. Well, we didn't have any more guns, so we had to terminate our trip, and we decided to head back to Milwaukee. On that drive, John and I decided to form a collaborative partnership. One of the two items discussed on the trip was the fact that John Bishop, the fellow who were working there, and we didn't have a method of rebuilding the guns. And this was the first obstacle in our path. Sometime after getting back home, I contacted Bob Wolfkill, the head of Southwest Vacuum, and we discussed our problems with respect to getting the guns rebuilt. As the conversation progressed, it became apparent that the major stumbling block to Southwest rebuilding the guns was that they didn't have any method of removing the old cathode assemblies from the grid cups. So if we could remove the cathode assemblies, Southwest would be willing to install new cathode assemblies and mount them on stems for us. The issues involved with removing the cathodes: we must be able to save the old 20-pin bases for reuse on the rebuilt CRT. The problem is the old bases are very brittle and easily damaged. The second thing is that the gun assemblies are very fragile. They're held together by glass rods called multiforms. Any attempt at cathode removal must not apply any excessive forces to the guns. Cathode assemblies are held in place by a retaining ring, which is spot welded to the inside wall of the grid cup. How do we safely remove the welds and the cathode retainer rings without applying any stresses to the gun assemblies? Task one was to save the base. After several unsuccessful attempts at base removal, the light bulb finally went on, and of course the KISS principle applied. To prevent breakage to the brittle Bakelite bases, I secured a standard 2-inch worm gear hose clamp around the edge of the base close to the neck glass. This hose clamp serves to restrict any forces that would break the walls of the brittle base. Here we see the clamp in place. First thing I do is I score the glass with a high-speed diamond ball bearer mounted on my Dremel tool. And then using a small side cutter, I apply pressure to the scores that I just made, cracking the glass. With the glass removed, I can snip the wires holding the gun assembly to the stem. At this stage, I use a needle nose pliers to smash the remaining glass that's inside the base, and then I use a mechanics pliers to crush the little pieces of glass that are hanging on the wires. Then I use a soldering iron to heat the pins and unsolder the wires, and then I drill out the pins with a number 55 drill bit. Then I use a utility knife and scrape the majority of the basing cement off the walls, and finally I clean it up with a little sanding drum on my Dremel. And here you see the salvaged base. This is the gun assembly as it was detached. This is an exploded view of the grid cup. From top down is the grid cup, and then the cathode spacer. This is the cathode assembly with a ceramic insulator around it. This is the cathode tube itself, and this is the cathode retainer. The cathode retainer is spot welded to the inside walls of the grid cup, and that's the issue we have to get rid of. We thought about grinding. Of course, that had been too stressful on the delicate gun. Torching it would have destroyed the darn thing. So I pondered the problem for a while, and I suggested to John that I might be able to remove them using EDM, which is electrical discharge machining. It would require making a precision fixture and a precision copper electrode. So I set about taking measurements and making a drawing and doing some close tolerance machining. EDM is the removal of metal through a process of erosion caused by a controlled discharge of electrical current through sparks emitted by an electrode onto the workpiece. I'm sure most of you have gotten a screwdriver across a couple of live wires and eaten a piece of your screwdriver away. Well, that was EDM in an uncontrolled manner. EDM comes in two forms. There's wire EDM, which is similar to a cheese cutter. in which a wire cuts a path through a piece of metal. And there's sinker EDM, which is what I'm using in this process. And sinker EDM takes an electrode that you've pre-machined to the shape of a hole that you wish to make into a piece of metal. And that's the original drawing that I made. I basically took one of the electron guns and a digital caliper, and I measured all of the dimensions of the gun assembly, and then I used basic high school geometry to develop tangents and drilling points for the machining process. And this is the EDM fixture that I made to hold the guns. It's made out of half-inch thick 6061 aluminum. There's a top view showing the strange shaped holes that actually hold the gun. And here you see a photo showing top-down view of the gun mounted in the fixture. When the cathode retainers were spot welded into the grid cup, the spot welding created a lot of craters on the outside walls of the grid cup. And those craters prevented the guns from sliding into those precision openings. So once again, it was back to the Dremel. With a diamond ball burr, I would smooth out all of the irregularities on the outside of the grid cups, and then eventually it would slide into the fixture that you see. The screws sticking out of the side are basically set screws that screw inward and secure against the walls of the grid cup just to hold the gun in place in the fixture. Here's a side view. And this is the EDM electrode. It's made from precision machined oxygen-free, high conductivity copper. That's which fits into the chuck on the EDM RAM, and the bottom end is precision machined to 0.488, and that end fits inside the grid cup with proper clearance so that it only erodes the cathode retainer washer. The cathode retainer washer is slightly smaller in diameter than the grid cup itself, so you don't actually do any erosion on the grid cup. You only erode on the cathode retainer washer. There's also a 3/16" hole in the face of the electrode in this area that's black, and you can't see it, but it's about 3/4 of an inch deep. Due to the fact that the cathode tube itself is isolated on a piece of ceramic, it's not non-conductive electrically, so you can't eat away at the cathode tube. So I had to make a provision for that cathode tube to slide up inside the electrode as it was being machined. This is the AGI Mondo 1 EDM machine at my brother's factory that we used. We normally use this to engrave images into hardened D2 coining dies, which we then put in a 250-ton press to strike coins and medallions. The EDM electrode is mounted into the vertical ram that you see above the orange tank. And the item that you're machining, which is called the workpiece, is mounted in a vise inside the orange tank and completely submerged in dielectric oil during the EDM process. This is a view of the process control monitor where you enter all the parameters for the job. You control the voltage, the current, the frequency, pulse width, duration of the cut cycle, the speed of the ram travel up and down, and a bunch of other parameters. The graphs are real-time indicators of how the EDM is processing. It shows the power being used to make the cut, the condition of the gap between the electrode and the workpiece, the relative speed of the cutting process, and the relative stability of all the sparks. There's also an XYZ axis readout to within 1/10,000th of an inch. In this slide, you see our fixture with the gun in the assembly mounted in the work vise, which is bolted to the tank. You can also see the copper electrode in the chuck of the EDM RAM. The process takes place submerged in a tank filled with dielectric oil, and here you see the tank starting to fill. This slide shows you the actual process taking place. Sparks are jumping from the surface of the copper electrode to the workpiece. The servo-controlled RAM is moving up and down according to the parameters set in the process controller, and when the electrode is close enough to the workpiece, the sparks start jumping across the gap between the electrode and the workpiece. Each spark creates a microscopic pit in the workpiece. The material eroded from the pit is flushed away in the EDM oil. The oil in the tank is recirculated through a filter pumping system, and it's trapped inside of a disposable filter, and that keeps the oil clean. The erosion time for each cycle is only on for a couple of seconds. Then the ram retracts to allow the debris in the gap to be flushed away in the oil. Then the ram lowers and the process repeats over thousands of times. As the electrode erodes the metal from the workpiece, the ram gradually lowers the electrode down into the work. It takes about 35 minutes to carefully erode the cathode retainer in each gun. Here we see the completed gun with all 3 cathodes removed. After removal of the cathode retainer, I manually extract the cathode and the cathode spacer from the grid cup with a needle nose pliers. On the left is the spacer. It sits against the bottom of the grid cup flange facing up. The job of the cathode spacer is to create a precision gap between the tip of the cathode and the inside face of the grid cup. On the right is the cathode from the business end showing the barium oxide. You can see an area of depletion in the center of the cathode tip. The cathode tube, which houses the heater, is made from nickel. The face of the cathode is sprayed with a coating of barium carbonate or a combination of barium, strontium, and calcium carbonate. When the heater is, when heated to 900 degrees centigrade, during the cathode activation process, the carbonate forms are converted to oxide forms of the compounds. It's the oxide forms of these compounds which actually emit the electrons when heated by the filament. After the EDM process is complete, the guns must be well cleaned to remove all traces of the EDM oil. I use a compressed air jet to blow off the majority of the oil in the gun assembly, and then the gun is subjected to 3 successively cleaner baths, each containing a gallon of methylene chloride. Any oil left on the guns would outgas when the tube is being evacuated, and that'd poison the tube. The final step in the cathode removal is to burnish the G1 grid cups. Years of heating by the old cathode and heater have left a residue on the bottom of the grid cups. For the finished guns to function properly, the bottom of the grid cup should be free of any contamination and smooth. To clean the inside of the grid cups, I use a Kratex rubber abrasive buffer. It's mounted in the Dremel tool. The rubber is compounded with various grits of abrasive. This photo shows the bottoms of the grid cups after they've been cleaned. Here we have 7 guns cleaned, polished, and ready for installation of new cathodes. Unfortunately, we don't have any photos of how that's done because Southwest Vacuum wouldn't let us take any pictures. It's all proprietary. So after the cathodes are installed by Southwest, the guns are mounted on new 20-wire stems that we provide to Southwest. At Southwest, they measure the flatness of the bottom and face of the grid cups. That tells them how tall of a cathode spacer to install. The cathode spacer sets the distance between the tip of the cathode and the inside face of the grid cup. For a 15 GP22, the distance between the tip of the cathode and the inside face of the G1 grid cup must be 45 10,000ths plus or minus a half 10,000th. No, plus or minus 5 10,000ths, I take that back. This distance is critical because it will determine the cutoff voltages of the gun, and for a color gun assembly to track properly, the cathode gaps must be alike on all 3 guns. In July of 2008, we decided to have Fredericks make another run of stems, this time with 3/8" tubulation. We reasoned that the stem cracking on the first batch was due to the fact that we had a 1/4" tubulation on the stem. By now, John and I had removed the many gun assemblies from leakers as we could get our hands on, and I had run them through the EDM process to remove the cathode assemblies. In September of '08, we sent 7 guns along with 7 of the newly designed Fredericks stems to Southwest Vacuum, and we instructed them to rebuild and mount 4 gun assemblies. This is a view of the new generation Fredericks stem with 3/8" tubulation. Our second trip to Hawkeye, John flies and Pete takes the train to Milwaukee. And on December 12, 2008, we drive through snowy conditions to Hawkeye with a van stuffed full of tubes and equipment. Steve McVoy flies in for the event. We believe we have the stem issue licked and we're excited. But once again, success eludes us. The new Fredericks stems are still cracking. We learn a valuable lesson. Never assume you've solved a problem until you test the solution. There are reasons for our lack of follow-through, though. We're aware that Scotty is going to be retiring before very long, and each time we pause to test to test something causes us long delays in our progress because we have to rely on Scotty to do all the testing. And for us, it also costs a lot of money for everything we do. But from here on in, we decided to start testing everything before we move forward. At this point, we don't understand the cause of the cracking, and all we can think of is that we have an incompatibility issue with the glass. Most old picture tube glass is a formulation from Corning called Old 12. It's common soda lime glass. However, it's no longer being manufactured by Corning. Fredericks tells us that they're using a glass that's compatible with Old 12 Corning, so we don't know what to think. And this is typical of the cracks that we're getting. And there's another good view. Those were taken by John. Well, we're disappointed, but we're having fun. During this trip, Scotty rebuilt the original 21A XP22 from my 21 CT55 set. It's a very early production tube that was made right after they stopped making the 15 GP22s. We're getting nowhere with Frederick stems because every stem cracks, and so we decide to cut our losses and go home. We decide we must scrap the batch of Frederick stems that we just had purchased. In January of 2009, we contacted Bob Wolfkill at Southwest Vacuum again. We told him about our cracking Frederick stems, and he suggested that we contact a vendor that they've been using called Richland Glass. We contacted Richland Glass and were hooked up with their production manager, Wayne Mason. Right off the bat, we can tell that this guy seems to have the right stuff. We send Wayne samples of the cracked stems from our last trip to Hawkeye for his examination, and using a polarimeter, Wayne can see stress lines in the stems all seem to be radiating out from the fillets, and he can see microfractures of the fillets where Scotty has bent the wires. Wayne says that they have made 20-pin stems for other customers in the past, and he finds some overrun in their inventory and sends them off to Hawkeye for testing. Scotty has mixed results, and the majority of the samples sent by Richland are still cracking. Okay, I gotta synchronize here. Failed Richland stems are sent back to Wayne Mason for evaluation. Wayne is still seeing the microfractures on the glass fillets where the wires exit the glass. The fillets are little glass nubs that the wires feed through on the stem. Wayne believes the way Scotty is bending the wires to allow them to fit into his sealing pin on the vertical lathe have something to do with the fractures. Wayne believes that the microfractures form the start of a crack, and then when the glass is heated and cooled, the change in temperatures causes the microfractures to propagate into a large crack upon cooling. We must find a way to make it unnecessary to bend the wires so the fillets don't crack. I decide we need a new sealing pin for Scotty's lathe. On the left, you see Scotty's standard sealing pin. This part sits in the arbor of his vertical lathe and holds the gun and stem assembly during the sealing operation. You'll notice that the angle of the funnel is rather steep. When the stem is placed in the standard sealing pin, the wires have to be bent at sharp angles in order to slide down the throat of that sealing pin. The new design is on the right. I machined a new sealing pin from a solid billet of bearing bronze. The goal was to achieve an interior angle that will allow the wires of the stem to easily slip into the throat of the sealing pin without having to be bent at a severe angle. The interior view of the sealing pin, this is the interior view of the sealing pin. The shallow angle in the throat of the new sealing pin allows the wires on the stem to slide down the throat of the sealing pin without pre-bending the wires. Unfortunately, although the new sealing pin is an improvement and better accommodates our 20-wire stems, it did not solve the cracking problem. April 5th of '09, while trying to determine the difference between the original RCA stem design and the Richland design, I discovered a curious thing. I came across the old gun and stem assembly that Scotty had removed from my 21A XP22 that he had built a couple months earlier. For some reason, it looked rather odd to me, and then it hit me. The stem had 20 wires on it, not 14 as you would normally expect. Evidently, at the end of the 15 GP22 production run, RCA had an overstock of 20-wire stems that they weren't going to use. So when they started the production run of the 21A XP22s, they mounted the new 21-inch Delta guns on the old 20-wire stems that were left in inventory just to use them up. This is this photo is the original 20-wire RCA stem that came off my 21 AXP22. Let's see. I took a good long look and compared it to the Richland stems, and the most apparent differences that I could see were that the fillets in the RCA stem were much larger, and the glass disc was thicker, and the RCA stem had internal chevron-shaped gussets leading from the fillets to the center of the disc. I suggested to John that we send the original 20-wire RCA stem to Wayne Mason at Richland for his examination. Wayne says for $250 they can modify the stem tooling that they use in their machine to make larger fillets and thicker glass. Jen and I give them some more money, and they make the tooling. Okay, in July 15th of '09, Pete Dexness makes a pilgrimage to Richland Glass to view and photograph the making of our new stems using our new modified mold. The wires used are special. They're made of Dumet. Dumet is a coaxial wire. It's made from a core of 41 to 43% nickel and 56 to 58% iron with additional trace elements. That core wire is encased in pure oxygen-free high conductivity copper. There's that tongue twister again. This special Dumet wire bonds well to the molten glass and makes an excellent vacuum-tight seal. So, starting with a Dumet wire and a little tiny glass tube, you slip the glass wire, the glass over the wire, and you populate the mold with the wires. Then you add a pre-flared 3/8 inch tubulation stem into the center hole of the mold, and you add a glass ringlet to the interior of the mold. Then you add another glass ringlet to the exterior, and these ringlets provide the necessary material when melted to form the disc of the stem. Now you light the gas flames and start heating the glass to the point where it turns cherry red. And then you close the upper half of the mold. The semi-molten glass gets pressed into a disc, and it fuses all the other glass components together. When you open the mold, this is what you have. Then you raise the part and you anneal it with the flames. You let it cool, and this is the finished stem. I want to thank Pete for making the trip over to Richland Glass to document this for us. This photo shows the 3 iterations of the stem development. The stem on the left is the first design with the 1/4 inch tubulation from John's first production run out of Fredericks. The stem in the middle is the second design with the larger 3/8 tubulation from Fredericks that we had to scrap. And the stem on the right is the final successful design with the 3/8 tubulation, large fillets, and thicker disc produced by Richland Glass. On July 30th of '09, we sent samples of our new design stem to Scotty for testing. Scotty mounts several of the new stems without any cracking. It appears that we have a stem design that works. We order another batch of stems to be made up, and on August 11th of '09, we sent some of the Richland stems to Southwest Vacuum. They were instructed to take 2 of the previously rebuilt ones and remount them onto the new stems. And on September 5th of '09, Scotty injured himself in a triathlon and he became out of commission. So we had to wait for a while. On October 23rd, '09, we received a long-awaited message from Scotty. The oven is on. Scotty has successfully mounted the new gun assembly on the 15 GP22 and it's in his evacuation oven. On October 24th, Scotty phones me with the best news we have heard to date. The tube survived the evacuation process and it's in good shape and it's holding vacuum. On the 26th, Scotty activated the cathodes and said that the gun was producing good emission. The tube is then shipped to John in Florida, and on October 30th, the tube arrived safely at his house. On October 1st, I flew to John's house in Florida and we worked for several days combating problems on the CT100 chassis. On November 3rd of '09, we are celebrating our first successful rebuild of a 15 GP22. This tube is producing magnificent, beautiful pictures, and we're powering the tube with John's Westinghouse chassis. But as we shall see, success is sometimes elusive. On February 22nd of this year, John flew into Milwaukee, and once again, we loaded up my van with tubes, equipment, and equipment for another trip to Hawkeye. On this trip, we carried 4 15 GP22s. 2 of them were leakers and 2 of them were under vacuum. Our intent was to rebuild the 2 tubes that were under vacuum and to mount stems on the 2 leakers for the purposes of leak testing. Scotty successfully mounted dummy stems on the 2 leakers, and he had no problem mounting a rebuilt gun on my under vacuum tube. However, the first attempt to put a gun on John's tube was met with failure. Well, we shrugged it off, took the gun out and remounted another gun, and that one was successful. And both tubes went into the oven. We placed these metal cake covers over the faces of the tube in an effort to prevent phosphor dot plates from cracking due to the penetration of radiant heat. Previous attempts have used tin foil, and we decided to formalize the heat shields by making formal shields. In about 2 hours, Scotty can tell that my tube has sprung a leak. Scotty shuts down the roughing pump on my tube, and we continue evacuating John's tube. When we open the oven the next morning and remove my tube, we find a catastrophic failure of the cover glass joint. We have Scotty give the cover glass a thump with a big rubber mallet, and the entire cover comes right off. We see the exposed innards of my trashed, once under vacuum 15 GP22 with the decorative mask removed. My tube had been treated with a special high temperature epoxy that we were experimenting with. It has an alumina filler, and it's called H74. We were attempting to ensure that no leaks would occur during or after the evacuation. As an experiment, we also placed a piece of window glass in the evacuation oven along with the 2 tubes. On that glass was a sample of 2 high-temperature epoxies. One was the H74, and the other was a sample of a product called 353ND. We removed the test samples from the oven. When we removed these test samples from the oven, the 353ND looked excellent. It showed no signs of degradation at all. However, the H74 sample was a complete disaster. When we turned the piece of window glass over and viewed the epoxy from the backside, we could see that the H74 had delaminated the glass like a fried marble. This delamination of glass by the H74 on my tube was probably the reason for the catastrophic failure of the cover glass. John's tube was also ruined. Aside from the fact that the stem cracked in the evacuation oven, which in itself is disappointing, but could be resolved, we discovered that the phosphor dot plate inside the tube had developed a crack. We're not sure why this happened. It may or may not have something to do with the cake covers that we use to protect the phosphor dot plate from radiant heat. We have no evidence one way or the other. However, it's evident that the crack propagated from one of the 3 alignment grooves that RCA grinds into the rear side of the glass plate. Future attempts will continue to use aluminum foil as was done in the initial attempts. Disappointed, we packed up all our stuff and headed back to Milwaukee. A few days later, on February 27th, John and I traveled to East Lansing, Michigan, where we met up with Pete Dexines. Our destination this time was the superconducting cyclotron lab at the University of Michigan. Am I going to get booted?
No, never.
Oh, okay. I'm reading as fast as I can. Fellow collector John Yurkon has invited us to examine our 15 GP22s for leaks using high-tech equipment at the facility. Our goal is to try and detect leaks and then attempt to seal them. Pictured here is the setup in John Yurkon's lab. It consists of a Varian helium leak detector and a tank of helium. The leak detector is a mass spectrometer that's tuned to detect helium atoms. Helium gas is used because its atoms are very small and they can squeeze through the tiniest of leaks. And helium is also extremely rare in the atmosphere, so there's very little background noise. There's a corrugated metal tube that connects the CRT to the leak detector. The procedure is rather simple. First, a roughing pump pulls a vacuum of about 10 millitorr or thereabouts, around 1,000th of an atmosphere, and then a turbo pump kicks in, and that can pull us down a couple more orders of magnitude. Then the operator squirts helium in the areas where you believe there might be a leak. When the mass spectrometer in the leak detector sees helium atoms in the vacuum stream, it activates an audio oscillator whose pitch increases in proportion to the number of helium atoms it's counting. It's very similar to the way a Geiger counter works. Response time is very quick. From the time the helium gets sucked through the hole in the leak in the tube to the time the leak detector sounds off is only a couple of seconds. With this methodology, it's possible to narrow down the location of leaks to within 1/8 of an inch or less. Here we see John Yurkon introducing helium through a nozzle into the areas where we might expect to find some helium leaks, some leaks, vacuum leaks, that is. John finds leaks in both the 15 Gs, 2 of which are in welds on my tube, and we find leaks on John's tube in spots around the Kovar flange. We also tested a 21AX P22 that had lost its vacuum that belongs to John. Once again, we found a leak on the weld flange. This is a close-up view. It's hard to see, but it appears that someone bumped the flange against some hard surface at some point and damaged the weld. When handling 15 Gs or 21AXs, be very, very aware of the fragile nature of the weld seam. Never place that seam against any hard surface. This is the inside of a turbo pump that's used in the Varian leak detector. They're very efficient. The turbine blades spin at around 40,000 RPM, and any gas molecules that get caught into the turbine blades are forced downward into the bottom of the turbo pump where they get concentrated, and then at that point they get sucked out by a roughing pump. This is a photo of our epoxy curing cabinet with a 15 GP20 inside of it. This is John's tube. We've treated it with vac seal. We're going to cure the vac seal in the cabinet and pump it down while analyzing the pump stream with a residual gas analyzer. The cabinet is electrically heated and can reach a temperature of 270 F. We also use this cabinet for curing epoxy resins. Here you see the cabinet in operation with the front panel in place. You can see the corrugated vacuum hose connecting to the port just below the RGA. This little gray box is the RGA, and it's connected by a cable over to this laptop. The RGA monitors the types of molecules that pass by its detector in the pump stream. It gives you a quantitative readout of what kind of and how many molecules of various gases it sees. By doing so, you can get an accurate idea of how the vacuum is progressing. Even with a big leak on my tube, that massive pumping system was able to pull 10 to the -6 torr, 100,000th of an atmosphere, which is the quality of a vacuum you actually need to make a CRT operate. Let's see. That's a view of the RGA monitor. It graphs, in this particular view, it's graphing nitrogen, oxygen, and water vapor. Our leak testing results. We were able to locate leaks on metal welds and on glass-to-metal joints. It appears that vac seal can seal the leaks, and we also feel that the 353ND epoxy will also too. Our leak sealing protocol would go something like this. Test for and locate leaks, mark locations, re-weld any leaks found on the weld line of the Kovar ring, mask and sandblast the Kovar ring and the glass, mix epoxy, and paint it onto the glass. Cure the epoxy in the cabinet and retest for leaks again. The equipment needed would be sandblasting shields, handheld sandblaster, a Lazy Susan platform, a digital gram scale, the epoxy, some paint brushes, an epoxy curing cabinet, and a TIG welder or a welder to do the welding tasks for you. These are EDPM roofing rubber shields that I made to place over the tube when we're doing the sandblasting. And we used 40-20 quartz and a little tiny sandblaster. This is the Lazy Susan with the tube sitting on it in place. And I placed the rubber dunce cap over the top of the CRT. We sandblast the Kovar ring and the glass. And that photo is kind of fuzzy because I'm behind a plastic shield. You remove the tube from the Lazy Susan and you remount and then you mount the flower pot adapter. That's just a plastic flower pot that allows us to turn the tube upside down. The purpose of the sandblasting is to create some tooth on the glass, and that way the epoxy will more readily adhere to the surface. This is the 353ND epoxy, the hardening agent, a little digital scale, some mixing cups, and a artist brush that we use to paint it on. And here you can see the way the tube looks inside of the curing cabinet. We only do one side of the tube at a time so that gravity doesn't cause the epoxy to drool off. So the one on the left is actually coating the back side of the Kovar ring, and the one on the right is processing the front side of the Kovar ring. And that's a picture of it closed. There's a electric heating element in that duct pipe. We salvaged it out of an old electric dryer heating element and modified it to run on 110 volts. It draws about 2,200 watts. This is a test sample of 353 ND epoxy that we cured in our oven for 30 minutes at 225 F. The product has an extremely high affinity for glass. After curing, I decided to score the back side of the glass and snap it in half to see how well the epoxy would adhere. There's the chip of the epoxy. It came off pretty much in one piece. It didn't crack, and you can see that it delaminated the window glass along with the epoxy. This is a view of that piece of window glass, and you can see the laminated section on the upper edge. As a side note, during our experiments, I had to remove 353 ND from several of our CRTs. There's nothing known that'll dissolve this stuff, and the only thing you can do to take it off is to grind away with it with carbide burrs on a Dremel. During the removal, the epoxy on one of the, it also chips away at the glass when you're doing this, and so during removal, I actually caused a crack to propagate all the way around the circumference of one of the rear sides. That tube is over at ETF, and the whole rear bell just came right off. This is a photo of the 353 ND that we sent through Scotty's oven, and it came through with flying colors. On March 12, 2010, I received a phone call from John. He was setting up our one and only successfully rebuilt tube to run off of a Motorola chassis that he'd been working on. The tube hadn't been operated in about a month, and when he fired up the Motorola chassis, he got a strong purple glow in the neck. The tube had gone gassy after less than 5 months. Our conclusions are that the electron guns are very rebuildable, but there's no telling if and when Southwest Vacuum may close. Hawkeye is closing its doors, so unless we develop an ability to rebuild our own tubes, they would have to be sent off to France to have racks do the work. Rebuilding the 15 GP22 should be accompanied by a strict leak detection and sealing protocol. Leak detection would require a helium leak detector, which could be quite costly. An alternative would be to seal every single tube and take the chance that there aren't any leaks on the welds. Even tubes that have been under vacuum for 50 years should be sealed, because the act of rebuilding and putting them through the evacuation oven can produce potential for new leaks, which is probably what happened to the tube that went gassy on us. We do recommend treating with VacSeal, although we have no evidence one way or the other if it will make much difference. John and I would like to thank you for all of the encouragement and support we've had over the last 2.5 years during this project, it was greatly appreciated.
Well, we'd like to thank you.
And I'm way over time. If you have questions, John and I will be very happy to answer anything in detail, but I have to move on, so.
John, take a bow, will you? Stop sitting there. John, how we doing, John?
We're doing pretty good, but we need more money.
Okay, tell us.
Our current count is at, it's only 1693, so we need a lot more.
Steve, is that enough for you to retire yet?
I'm already retired.
Yeah. Look, we're going to go into a short break for whatever you want to do for a short break, and we'll yell at you to reconvene and come back, and now's your chance to talk to Bob and John about their progress. And let me make one commercial announcement. I've got a CT100 with a great tube, and I'll show you screenshots if anybody wants to buy it. I got too many. Almost sold. He bid 100. What am I going to do, Pete?
You ship it for that price, right?
I'll deliver it on my bicycle. Oh, now you guys fixed it. We're scared to touch it. What the hell? As long as you don't drop it, you can't break it.
Breath just listening to all the back and forth, working on this.
Friends, friends, take your seats. Take your seats, please. Yeah.
One more thing I forgot to tell you. We are almost going to be super fine on time. So John Folsom, after Lloyd's presentation, is going to make a 10-minute presentation on rebuilding flybacks, rewinding flybacks. He's been successfully doing color flybacks.
All right. Oh, holy shit.
Yeah, right. And John was reluctant to do it, but I twisted his arm and he's agreed to come up talk for 5 or 10 minutes about how he does it. So,
But you don't have to send them to England anymore.
well, no, nobody could really do them. Nobody could do the high voltage winding. But John, he showed us.
This is that little lady that was rebuilding